So next, what we are going to do, we are going to talk about another very interesting application of definite integrals, which is about computing the volumes of the different objects actually. So yes, through the definite integral, you can also compute the volumes. Volumes of the non-standard shapes actually. We know the volumes of some of the shapes. So for example, we know what is the volume of cylinder, we know what is the volume of cube, we know what is the volume of sphere actually, okay. And now we would like to talk about, for example, volume of some of objects which are, neither cylinder, nor sphere, nor a cube. So it's like, something like, for example, this bottle actually, okay, or maybe something like something else, okay, that you are interested in computing the volume, that how to compute the volume of such kind of objects. So let's start with making sense of the basic formulas of the volumes, okay. Before getting into what do you call the actual theory, I would like to make you realize that why the basic formulas, say for example about cylinder, is the way it is actually, and why say the volume of, say for example, cuboid is length multiplied by width multiplied by height actually. Why these formulas are like that? Because once you understand this basic philosophy, the same philosophy also applies to the complicated kind of objects actually. So let's just start with volumes. I would say even let's start with the basic area actually. I know that if I have a rectangle, okay, a rectangle, that rectangle has say width of say W, say centimeters or whatever, and L is the length of it actually. Then we know that the area of the rectangle is length multiplied by the width actually. But the question is why it is length multiplied by the width? The answer is, so I mean, most of the time we kind of treat this as the basic given fact actually. Does it have an intuition? The answer is yes, it does have an intuition actually. So what is that intuition? The intuition is this. So if this is, what do you call, this width is W, okay, centimeter or, millimeters, whatever you call it. And so essentially what you want to do, you want to fill this area with something. So what I'm going to do, so I'm taking say a stick actually. So assume that this yellow line is like a stick, okay, that has a unit width actually, okay, that has a unit width. Its length is L, okay, but its width is 1 actually, okay, so 1 unit, okay. The question is, how many such sticks you need to fill this entire, what do you call, this entire region? The answer is, so I can do what? I can fill, okay, I can fill this entire region by such sticks actually. So these are really the sticks. Let's assume that. Where each of the stick has length L and width, say, really tiny, let's call it, it's a kind of a unit actually, small unit. So how many sticks you need to fill this entire area? So if this width is W, that means that you need W, what do you call, W sticks to fill this entire area, where each stick has length W. So in other words, so why you have this L times W, so you can also treat this as that, so since you need the W, what do you call, sticks of length L to fill this area, so that means this area is going to be roughly. So I'm just giving you an intuitive picture. This is not a rigorous argument. I'm just giving you an intuitive picture actually, so that you should make sense of this actually, that why this formula is like that. So it's like if you add these lengths, okay, these lengths, these sticks of the lengths actually, but how many sticks you need to fill this entire area? So you need, you know, really the W such lengths actually. So W times, so you need to add these L's, these sticks of length W times in order to complete, to fill this entire area. And what is the meaning of adding a number W time? So the meaning of adding a number W times is like multiply it with the W. It's like multiply it with the W, and hence roughly you get the area of this rectangle to be length times width. Okay, so why the area is length times width? That you need the W sticks of length L to fill this area, where each stick covers the area of L. So if you sum them up, that would be the area covered by the all W sticks actually. Okay. There is a cheating in it. I know that in this argument there is a cheating, so, but I'm not focusing on that cheating, just to give you an intuition actually. Now let's move towards, instead of taking, for example, a rectangle, let's take a cuboid actually, or maybe a cube. Okay, so let's take a cube. Let's take a cube or a cuboid. And how do you compute the area of this cuboid? Okay, the area of this cuboid is that, okay, if this is the width of the base and this is the length of the base and this is, say, height of the base, then the volume of this cuboid is length multiplied by width multiplied by height actually. Why it is the case? You can understand it, for example, through the example of this book actually. Okay, so this book has, so you can treat this book as a cuboid. Okay, so you can treat it as like a box actually. What is the volume of it? I know that I can easily calculate the volume through this formula, but the question is, what justifies this formula? So the justification of, rough justification of the formula is this. Okay, it's not rigorous but a rough estimate. So if you, for example, what is the area of, say, this cover page or one page of this book? So it's going to be, for example, length multiplied by its width actually. So this is going to be the areas. But I can treat this box as a lot of such pages staked on each other. So like this is page 1 that has area length multiplied by width. This is page 2 that has an area, you know, length multiplied by width. So if you put a lot of pages together, okay, a lot of pages together on top of each other, you're gonna get what do you call the volume of this object. So in other words, in order to compute the volume, I need to add these basic volumes. So if I ask from you, what is the volume of this page actually? So I'm gonna say, okay, you know, it has, for example, this area length multiplied by width, okay, but it has really a really negligible height actually, okay, a really negligible height. So its volume, let's say that this area is really, what do you call, length multiplied by width. And if you add, so this is first page, then if you take second page, you can do the same with it, length multiplied by width plus so on and so forth, length multiplied by width. Okay, but how many times you have to add it? You have to add it as much as time, as much as is, what do you call, the height of this book actually. Okay, and say what is the height of this book. So in other words, you need to add this sum h times. So what you're going to get? The net sum is going to be length multiplied by width multiplied by, what do you call height actually. So this is going to give you the volume. Okay. So each page is like length multiplied by width and say a unit of height actually. Okay. So if you want to compute this net volume, so what you can do, you can add the volumes of all these, what do you call, pages to compute the volume of this entire, what do you call, box or the book actually. So in other words, you need to add these volumes. This is not really area because you have length multiplied by width multiplied by 1 plus 1 is the unit height actually. Okay, length multiplied by width multiplied by 1 up to length multiplied by width multiplied by 1. So all these are the volumes of each one of these pages. And if you add the volumes of all these pages, you're going to get the volume of the entire, what do you call, book. Okay? And this net volume is going to be, because you are adding these pages h times, as many pages you have. So h is representing that how many pages do you have in this book. You add the volumes of all of these pages and you're going to get the net volume to be length multiplied by height multiplied by, what do you call, length multiplied by width multiplied by height actually. So in other words, if I have to compute the volume of this object, I have to consider this object as the set of, what do you call, small pieces, okay, small copies of the same thing stacked on each other. Now, how about cylinder, for example? So we know that if you have cylinder, this is really intuition, okay? Because the same intuition would work if you have more complicated picture. Okay, this is intuition. So if you take, for example, cylinder. Now we know about the cylinder that its area is pi r square h. Its volume is pi r square h. Question is why it is pi r square h. Okay. You can treat this, what do you call, cylinder, okay. So this is like a solid cylinder, a filled cylinder, okay, as what do you call, the discs sitting on each other actually. So one of the easiest example that I can give is that if you have seen the stacked bangles on each other, चूड़ियाँ देखी होंगी आपने. So you must have seen the चूड़ियाँ. So the चूड़ी, so each bangle is like a ring, but if you put another ring on it, so if you put another bangle on it, if you put another bangle on it, so these collection of the bangles will form a cylinder actually. Okay, the collection of the bangles is going to form the cylinder. Now each bangle is what? So each bangle is like a disc actually. Okay, is like a disc. And what is the area of the disc actually if the radius is r? So the area is pi r square. So how many bangles you need to fill this entire cylinder? You need h bangles to fill this entire cylinder actually. So in other words, take the h bangles, put it on each other, where each bangle has, what do you call, area pi r square, okay. And if you multiply this by 1, this would be the volume of each bangle. So if I treat, that each bangle is, say, 1 unit high, okay. So how many bangles you need to create a cylinder? You need really, what do you call, h bangles to create the cylinder actually. So in other words, you need to add the pi r square h times to get the volume of the cylinder. So no matter what picture you take, okay, so the idea really is that if you take a picture, if you take a complicated, what do you call, object, and you want to compute its volume, slice it into the sections, slice it into the pieces, and then compute the volume of each piece and then add all these volumes together. So you're going to get the volume of the entire object. For example, I can talk about say the volume of, say, this bottle actually. So if I can come closer actually, I mean, if you see in this bottle, I hope it is visible that, so it's like if you consider this bottle as one single piece, okay, in which you can fill the liquid or things, okay, so it encloses a volume actually. Now in order to compute the net volume, what I can do, I can, you know, slice this bottle into the pieces actually. So this each ring is like representing the one slice, okay, representing the one slice. Now what would be the volume of each ring? So I'm gonna say this each ring has a base like circle. So this is like a disc actually, okay, which has a little height, okay. So this is the height of the disc, and what is the area of the disc? It is pi r square. So what would be the area of each one of this ring? So it's going to be pi r square h. So if you add all these rings, the volumes of all these rings, put them together, you're going to get the volume of the entire bottle actually. So this is essentially what is the idea that we are going to act upon, okay. So what we are going to do, I mean, obviously these rings has a lot of height actually. So now we're gonna apply the calculus. Like for example, when we were trying to computing the area, first we took the big rectangles and then we said that let's shrink the size of the rectangles actually. So we're gonna do the same. So first we are taking like these big rings, and then we're gonna assume that the height of ring is, you know, reducing actually, okay. So these are really, you know, really tiny disk actually with a minimum of the minimum height actually, okay. And then you have lots and lots disks put together, and this sum is going to give you the volume of the entire picture actually. So let's make an abstract picture, and let's try to show you that, you know, what actually I am saying actually. So let's imagine, you know, this is something like bread actually. So imagine this is, you know, the cake that you have been eating in the morning, you know, when you were a kid actually. At least I was eating when we were kids. So the cake, you know, kind of looks like this actually, okay. So it looks like this, something like this, okay. So something like this, and so this cake is like the filled cake, okay. So you may treat it as like a bread actually, that this is bread, okay. So this bread is a kind of a solid object actually, okay. So it's not hollow, it's not empty, so there is a stuff in it. Now if you want to compute the volume of this bread, okay, the idea really is that, okay, consider a slice of the bread, you know, break the entire bread into the slices. For example, one of such slices is this actually, okay. So when you're gonna slice, so this is one. So in other words, so I took this bread and then I'm cutting it, okay. So I'm cutting it with, for example, I'm cutting it, say for example, knife actually. So what I'm gonna get a copy of this shape actually. So I'm gonna get a copy of this shape, okay. So let's do another cut, okay. So let's do another cut. So this is another cut, okay. So when you're gonna cut it, so this is really like a piece of the bread actually, okay. So this is one bread, okay. So one little cake that you get after, you know, cutting into the two pieces. So what we can do, we can break this entire bread or this arbitrary volume into such loaf of breads, and if you put the volumes of all such loaf of breads and add them, you're gonna get the volume of the entire entire bread actually. And how to compute the volume of this loaf of the bread actually, okay, of this arbitrary picture. So if you see the top view of this, the top view is going to be something like this. So from top, it would look something like this actually, okay? But it has some thickness as well, okay? So it's not something that is, so it has some thickness as well, okay? My drawing skills are not so good, but I hope things are making sense to you. So it has some thickness as well. So this is really the thickness of the bread, okay? This is really the thickness of the bread actually. The loaf of the bread, the piece of the bread, okay? So if I say this area of the cross section, when you cut it, when you slice this, the area is becoming, for example, A, and say the width of it, okay, is some, so it has some height actually, it has some width actually, okay? So if this height or this width is say W, then the volume of this loaf of bread is going to be A multiplied by, okay, A multiplied by W, A multiplied by W, okay? This is what that we're gonna get. Now, let's do it a bit more formally. Let's do that. How this slicing, how can I slice, this entire picture into small pieces, and then the small loaves of the bread, and then put them together to compute the volume. So let's imagine that like this loaf of bread is sitting inside XY axis, okay? It's sitting inside XY axis. And let's imagine that like this guy exists between A and B, okay? So it exists between say A and B. So what we can do, that we're gonna do the same. So let's break first this entire interval into say n pieces, okay? So this is one piece, another piece, another piece, another piece, and then later we will going to increase the piece actually, okay? I'm gonna increase the piece. Now the width of each one of this subinterval is really delta x. So each subinterval has width delta x, okay? Now corresponding to each point, say for example, if I take this, so treat this as that you are taking, for example, knife and slicing it, through this point. So when you're gonna slice this bread through this point, what you're gonna get? You're gonna get the copy of this picture actually, okay? So you're gonna get the copy of this picture. And next, say slice it through this point actually, okay? So let's slice it through this point. So when you're gonna slice through this point, you're gonna get another copy of it, okay? So you are looking at the side view. You are looking at really okay. So you're gonna get something like this. So in other words, on each subinterval, you have a slice of this volume actually on each subinterval. Okay, I mean you can see this picture more clearly in book. Okay, but I'm trying to depict it actually. I'm trying to depict it here actually, where each blue line corresponds to the red line. So hence what we can do, so to each subinterval I'm gonna get a slice of a loaf of, say for example, this bread, and if you put all these loaves of the bread together, you're gonna get the entire bread actually. Okay, and as I said, if I compute the volume of each of the bread actually, so if you want to compute the volume of the loaf of the bread, for example, if I redraw that picture again and see the top view of it, okay, so this is one loaf of the bread, okay, one loaf of the bread, okay. Now the area of the cross section is A, and what is the width of this bread? The width is the interval, okay, so the width is really the interval actually. So on this interval you have, for example, this actually, okay. So the height, if you say the height of it is really the interval. So the volume of each slice is say A of x, okay. So the volume is area depending on x multiplied by delta x. And say for example, this is the ith slice actually. So you can have n such slices. So let's assume that ith such slice. So the A of I is representing the area, and delta x is representing really the height or the width of what do you call this loaf of bread. So if you multiply the area by its height, okay, so you're going to get the volume actually. And if you sum all such loaves together actually, okay, loaves of the breads together, so what you're going to get? So in other words, let's in how many pieces, for example, I have broken it. So I have broken it into, say for example, n subinterval, okay. So these are n subintervals. So if you put all these volumes and volumes of these loaves together, you're going to get the volume of the entire picture actually, okay, approximately. So this is going to be approximation. And how can I get my approximation better and better? By creating more and more what do you call subinterval. In other words, slicing this bread into more and more thin pieces actually, making what do you call making the loaf of bread more thin and thin and thin, okay. So that is going to give you, so for example, as I give you the example of the page actually, so make each loaf of the bread like, thin like the page. And when you're going to put all these pages, in other words, all these loaves together, you're going to get what do you call your required volume of this piece of bread actually, okay. And how can I do it? In order to do it, you can take the limit. So if I take the limit, n goes to infinity, I equal to 1 to n, I of x, delta x, this would be my volume. But this I can write as an integral actually. Okay, I can write this as an integral. That okay, the area of the subsection multiplied by its height, okay, or its width or its thinness, okay. So when you're going to multiply these, so if you sum all these volumes from A to B, you're going to get the volume of the entire loaf of bread actually, okay. So this is a generic picture, okay. This is an abstract picture. This picture could be a cylinder, it could be a cube, it could be it could be a bottle, it could be anything. It could be anything. So that's the formula that we're going to use now on to compute the volume of any given cylinder, okay, or any given picture. So the method is going to be what? We're going to take that picture, slice it. By slicing, I'm going to get an area, okay. So we will try to find the formula for the area, and once you have the formula for the area, just integrate that formula, you're going to get the volume actually, okay, you're going to get the volume. So that would be like you took those areas, cross sections, stacked them on each other, and you get the volume. You get the volume. Like the bangle, for example, and cylinder. You take the different bangles, put them together, you're going to get a cylinder. So all these are the approximation kind of techniques. So I hope that you got some intuition for the formula. Even as I said, through this formula you can compute these formulas as well. So let's start and say compute